Okay, so we are live. Welcome everyone. For this tutorial, we'll see about how to apply linear transformations and also how that relates to the solution of linear systems and the concept of invertible and non-invertible system. This TA will be a little bit shorter than usual because I know that you're probably busy with your homework, so it will be shorter than usual. Okay, first let's have an image. Okay, in each pixel of this image, you have associated a position. For example, in the eye, let's say that there is the 0, 0. When I go to the margin here to the right, this one is 1, 0. At the top is 0, 1. And here is 1, 1. Okay, so in this code block, I just define an image. And there's multiple types of linear transformation. A linear transformation of the coordinates that I was just talking about. And one of them is the scaling. And when you're trying to do a scaling operation on an image, basically you're just modifying the diagonal terms of this matrix. Here I have an example with the matrix 1/2, 1/2, and 0 at the other sides. When I apply this linear transformation to the coordinates of the image, you can see that this results in a shrinkage of the image. The image is now smaller. Don't worry about these copies. This is just the way I'm showing it, but the correct transformation is just this center image being smaller. If instead of doing 1/2, I do 2, that results in a zoomed image instead, right? So maybe just to start, let's see why that happens. Wait me a second, I'm looking at the pencil of the tablet. Okay. So in this case, I'm showing an image as a representation of a space. So the space, let's say we have R2 with components X and Y. And my image is somewhere in this space. Let's say it's a smiley face. Each of these pixels or positions in the image have a vector. Let's say the vector is X, Y. And if I apply a linear transformation to this vector, let's say a scaling linear operation like 1, 2, 0, 0, that results, after the matrix multiplication, this times this is equals to the first element. In this case is just X, and then this dot this is this element, and I'll have 2 times Y. So from a vector X, Y, I transform that position to X, 2Y. The starting vector is in green, and the resulting vector, I put it in orange. Here in orange. So the x is the same, so it will remain in this position. And the y is 2 times the first one. That means that the resulting point will be something like this. X, 2y. After applying this transformation to every pixel, what we'll have is that our image will be enlarged in the y axis. So the eyes will be bigger, and the smiley face will be like right here, down here. Okay, so that's why if I do a linear transformation with 2, 2, I will get an expansion. If I have 1/2 and 1/2, I'll shrink the image. And if I do, for example, 2 and 1, I will enlarge the x-axis, and the y-axis will remain the same. That's why it's bigger in this direction, like that. And doubts about this? Yes, no? Clear? Let me see the chat. All clear? Okay. All the notebooks of the labs are in the course website. If you go to cursos.canvas.uc.cl, mathematical methods, there's a section here called tutorials. Tutorial 1, have the code here. Tutorial 2 here. This is the tutorial 3, the tutorial 4 is here. And by pressing this link, you'll go to Google Colab. And you can start messing with the code here. Okay. Another type of linear transformation that is very common is a rotation. To explain why the rotation is characterized by this matrix, let's go back to the drawing board. And let's say I have a coordinate system in 2D, x and y, and I have a vector here called x hat, and I want to rotate this vector with respect to the z axis to this direction in an angle of theta. So the resulting vector will be like here, x hat prime. If we do a zoom, like in CSI, to this part, we have that. Have the vector x hat prime. We have the vector x hat, the angle theta, and let's say that this is 1, 0, where it will land after the transformation. What is the x component of this x hat prime?
cos theta.
This one is the cosine of theta. And this one, the y component.
Sine of theta.
Yes, sine of theta. Okay, now let's do the same, but with another special vector. That is this y hat with coordinates 0, 1. After the rotation, it will land somewhere about there. This is the y hat prime. This is the angle theta. If we do the same, we have y hat. We have y hat prime with this angle. So let's do the same, but for the x component of this y hat prime.
Minus cos theta and sine theta.
Okay, so let's see at this angle. This angle, theta, the sine would be this length, right? But as you can see, it's pointing to the other direction, to the left. So that's why the first component, x, is minus sine of theta. And the y component is cosine. It's minus sine and cosine. Okay, so why am I doing this? Because we know that the rotation can be represented as a matrix. Also, we know that if we put the vector x hat to this matrix, it will give us x hat prime, and we have also that a dot product with y hat is equal to y hat prime. So can someone tell me the matrix now? Let's start with the first component, this one. Okay, so let me write this again so you can see the relationship more clearly. This is A, B, C, D. When we do it with x hat, we are basically doing 1, 0. And that is the same as cosine and sine. Then to the same matrix, A, B, C, and D, we apply y hat, or 0, 1, and that's minus sine of theta and cosine. So if we look at this, and we do our matrix vector product, for the first component, this, will be this. So that's A. And for the second component, we have this and this. Sorry, here. And we have B. Sorry, C. On the other hand, here we'll get B and D. That means that our first component here is cosine. The second component here will be minus sine, and so on, sine and cosine. Like that. So that's why the rotation matrix is this one. Are you following me? Or should I explain something again?
Again, please.
From where? From this, from this, from this? From the start?
From the vectorial equations.
This one?
Yes, please.
Okay. So we started with x hat, this red vector, and y hat, this green vector, right?
Right.
We know that the rotation matrix is a matrix, obviously, that when applied to any vector, it will rotate that vector in theta degrees. So we start with the red arrow and the green arrow, and this will rotate the red to the orange, and this light green to this darker green arrow. Okay? So
Are perpendicular these x hat and y hat or not?
yes,
In the beginning, yes. Yeah, and
the red arrow and the green arrow are perpendicular, and after rotation they are perpendicular as well.
Okay.
Now, if we analyze only the red vector here, let's put a 1 here, you see that after the rotation in theta degrees, the vector will arrive here, and by just basic trigonometry, we can see that the x component is cosine and the y component is sine. Okay? Do you see that, or should I explain it further? Why this is sine and this is cosine?
No, clear.
Okay, so we do the same with the y hat, but instead of remaining in the positive quadrant, it goes to the left, and that means that the x component is minus sine by the same trigonometry, and the y component is cosine. So this vector here. That means that our matrix applied to x hat equals to x hat prime, and the same with y. Let's remember that A is simply A, B, C, D, or any numbers in a 2x2 matrix that after applied to the x or 1, 0 resulted in cosine and sine. If we do our matrix vector multiplication without considering this orange part, we see that the dot product between this and this will give us A, and then will give us C. That means that A equals to cosine, C equals to sine. If we do the same with y hat here, we can infer that B, or this component of the matrix, is equal to minus sine, and d is equal to cosine. Basically, by applying these unitary vectors, we're getting the columns of the matrix. If we wrote it as A is equals to a vector A1 and a vector A2, by applying 1, 0 to this, you'll get A1 that is the same as the first column, and by applying 0, 1, that means the result is A2 or the second column. So that's why the rotation matrix is like this. Is it more clear now, or?
Yeah, to me, yeah. Thank you.
Perfect. So now let's see how this behaves in our image. I put cosine minus sine, sine, cosine, with the angle pi over 4. And after applying the rotation, you can see that the image rotated in 45 degrees. Pi over 4 is the same as 45 degrees. We can also do it in pi third over 3 and give us another angle. If we do pi or minus pi, it will result in an image upside down. And if we do 2 times pi, that is the full rotation, it will remain the same. But let's leave it at this. Right. The last one I wanted to see is the shearing operation. That is not as trivial as the other ones. And basically what it happens is that if you have your image, it becomes slanted to one side. If I put the shear coefficient here, it will become slanted to the right or in the x component, but if I put it here, it will do the same but in the y component, so like this. And why this happens? Because if we look at our matrix 1m 0 1, and we apply our x and y, the result will be x plus my, and here it will just be y. And if we do a little drawing here, if I have a vector x hat that's equal to 1, 0, the result of that would be the same position. But if instead I have here y hat 0, 1, I will get the resulting vector m, y, y. The y will be the same, but it will be a little slanted like this. In this case, the solution would be m, y, y, like so. The same would happen to this vector, and so on. So that's why it goes like this. Did you go follow me with the shearing operation?
And if you change the m variable, please.
Okay, so for example, if I do .5, it will be a little to the right. But if I put, for example, 2, it goes like like a lot. If I do it to the other side, instead of going to the right, it will go to the left. And if I put 2 here, it will be a very big shearing to the left. If instead of putting the m here, I put it here, it will be the same, but in the y coordinate. So let's reduce like this. It's going down. If I do a negative m, it's going up. Okay, so let's continue. I have a question for you now. Would you say those linear transformations are invertible? Another way of asking this is that if I give you this image, could you retrieve the original image? Let's start simple with the scaling operation. Could you retrieve the original image from this? Jorge thinks yes. Okay, so for scaling, I think we all agree that you can recover the original image from this. What about this? If I gave you this image, also, but what happened to the details that are outside?
Yeah, they kind of lost.
They get lost, right? So that's not the fault of the scaling transformation. That's only the way I'm plotting it. I'm plotting it in the same space that the original image. So if the image goes beyond that, it's not shown in this example. But the linear scaling, it is invertible. The details will be outside, but you will have no loss of information. Now for the rotation, if you have something and you do a rotation, could you tell me how the original was?
By applying another rotation in the another sense.
The rotation to the other side. Yeah. That's very important because we just found out, just by thinking a little bit, if you rotate something to the other side, you are doing the opposite effect. That means that if I have a matrix A that is equal to cosine of this minus sine of this, sine, cosine, and if I apply this matrix to xy, I can later apply another matrix that is the same rotation but in the other side, or with the negative angle. That means that this would be cosine of minus theta minus sine of minus theta, and the same for all the other components. And this rotation in angle theta and this rotation in angle minus theta, they will cancel out. Let's look a little bit more about the red matrix here. I'm not sure if you know, but just a reminder, you have the functions cosine. They look like this. This is a cosine of theta. If I do the same with the sine, it would be like that. So basically the sine of theta is the same as the cosine, but is shifted to the right. Now let's see what happens to the cosine of minus theta. The cosine of minus theta, or that means that we have a function evaluated in minus the argument, is equivalent to flipping the plot with respect to y. So the cosine will be reversed in the x direction, and we can see that cosine is equal to the cosine of minus theta. If we do the same now with y, we can see that the resulting function sine of minus theta is the same as the sine, but with a negative sign. Like this. So after flipping with respect to y, it's the same as the sine of theta, but flipped with respect to x. It's a little bit confusing, but look at the plots. That means that the sine has a very special property that when evaluated with minus x is equal to minus sine of x. That's the definition of an odd function. Odd functions satisfy that f of x equals minus f of minus x. Cosine, on the other hand, is an even function. Because it satisfies that f of x equals to f of minus x. If we apply those principles, this is a reminder, so I will put it in a cloud. Like that. If we apply these equations to the rotation matrix, we'll have that cosine of minus x or theta goes from minus to just theta. This minus sign goes to the outside and cancels out. Sine. Here it will go to the outside. And here will remain the same. Is there any relation between this matrix and this one?
the inverse, no? Or not?
Yes, one is the inverse of the other one. So you could say that r of minus theta is equal to the rotation to theta inverted. That could be expressed also as r of minus theta times r of theta equals to the identity matrix.
Yeah.
But there's another relationship. That's one of the relationships. Can you see any similarities between this one and the other one? Could this be expressed as something of the other one?
The transpose, maybe?
Exactly. So the inverse of a rotation matrix is equivalent to rotating to the other side, and that is equivalent to the transpose of the matrix. So the second thing that is particular of rotation matrices is that the inverse rotation is equal to the transpose. Okay, this is very important. So you have that, and you have that. Right. Yeah, everything okay? Are you following me with this?
Yes, but I don't remember the translate for the odd function and even function.
Do you want me to explain a little bit more about this?
No, the translate of the odd and even.
In Spanish?
Yes, please.
Okay, so even is par, función par, like the numbers.
Ah, yeah.
Odd, impar.
Okay.
Let me put it here. Even, in Spanish is par, odd is impar. That's the meaning of those words. And transpose is transponer. And to go from this to this, we applied this star. Okay, so we not only see that the rotation operation is invertible, but we found the inverse, and we can write the inverse with respect to the normal rotation. Jorge, do you have a question?
Maybe if always work for another function and not only for the trigonometric function. If the property 1 and 2 work for another function, odd function and even function.
If this cosine is a even function and this sine is a odd function, it would have almost the same property, that the minus theta equals to the transpose. But the connection that case would miss is that minus theta is the inverse. And that's a special case of the rotation, because doing it to one side and to the other, just by logic, you can see that it remains the same after that. If you have a more complicated function or transformation, maybe that's not the case. So these are special properties of the rotation matrix. Maybe not the second one, but the first one.
Thanks.
Okay. The shearing, do you think is invertible?
I don't know. I think it's like out of plane transformation, but maybe it's my point of view from.
Yes, you are correct. After applying this shearing transformation, some parts of the image goes outside, so they are not visible anymore. But that's just because I'm plotting it this way. It's not an intrinsic property of the transformation. So if you had the whole image outside the first 1x1 square, you would still have the information about the image, but in other parts. So just by applying the same logic, if you can still have all the points, you can sort them out and find the original image. So this also is an invertible transformation. Now I have another question. Every linear transformation is invertible? If I have any transformation that could be represented as a matrix, is that invertible?
Maybe depend of the if the function is injective or not.
Yes. That's a way to think of it. Sorry, some of you are trying to access this Google Colab. Are you able to access, or I have to give you a special access?
I think you need permission to access the Google Colab.
Okay, let me fix that.
So, Carlos, about your question, it seems that if you have like the all information from, in this case, from the picture, it's possible that the process of the transformation is reversible.
Can you repeat that?
So, about your question, if every transformation is a reversible process, it seems that if you have all the information after a transformation, is a reversible process, I guess.
Yes. And how can we express this loss or no loss of information in a mathematical way? Or can you think of an example in which this image would be transformed in a way that you would lose information?
When you compress an image, maybe, or you want to reduce like the quality, for example?
Yes, that's a way to do it. The compression of images is in fact, it could be represented as a linear transformation. Not in the same sense that I'm showing here, but yeah. And there's a lot of there could be compression processes that are lossy, or you have a loss of information, yes. But to do that, you need to do an additional operation, like removing some coefficients of the representation and stuff like that. And that's not linear, but it's a good example of something that could be lossy.
And when you reduce the information to the binary code, for example?
Yes, that's also an irreversible process. If you have, let's say, an image and you want to reduce the number of bits of the image or the number of quantization steps of the image, let's say you have a signal like this, and you want to quantize the image, let's say in these 3 values, you would have something like and clearly after that you cannot go back to the original function. But this is not linear, applying this. But it's a good example. Quantization. So those are lossy but non-linear. Linear. Another example was the compression of images. So if, for example, you have a smiley face, and after that you transform that image to a JPEG, and it gets a little bit blurry, that's a lossy compression. There are another formats that are not lossy. For example, the PNG or bitmap. So if you want to have the quality of your image but reducing the size, you can compress it to other formats, but not JPEG. JPEG will always reduce the quality of the image. But that's a non-linear process. It applies a linear transformation, yes, to the image. But after that, it removes some coefficients or data and then gets the compressed image. This, by the way, is the image. And this is a matrix that represents the wavelet transform. And the wavelet transform, it's in fact a linear transformation. But after applying the thresholding, that will represent with TH, it becomes a non-linear operation. There are very simple lossy transformations that are linear. Linear lossy. Can you think of one? I'll give you an example. What happens if I have a matrix? I have X and Y, and it do the same, or the X component remains, but the Y component disappears, like this. This is in fact a linear transformation, but there's a loss of information. With an image, this would look like having this smiley face, and after the application of the linear transformation A, you would have just the image but compressed to one dimension. So you in fact reduced the dimensionality. So this matrix A is linear, is lossy, and therefore is non-invertible. And why is non-invertible? The engineers, can you give me the reason? Or the non-engineers, or whoever knows the answer. What's the particularity of this matrix that makes it non-invertible? Sorry, can you say that again?
Determinant is
its determinant is
different to 0. No, it's different to 0. Determinant not.
Okay, so one idea is that the determinant of this matrix A is equal to 0. And that's correct, the determinant is equal to 0, because the determinant of a matrix in 2D is the same as multiplying the diagonals and then subtracting the anti-diagonals. So it would be AD minus BC, that in this case it would be 1 times 0 minus 0 times 0, that is 0. So that's correct, but that is not exactly the reason. There's another reason that makes the determinant goes to 0.
Maybe it's the same in like the last example that you used the transpose of this matrix, but in this case you couldn't get like the other component.
You can calculate the transpose of this. You would get the same matrix, but that's not the problem.
Maybe the matrix A have not inverse element, so
yes,
you cannot to get a 0 vector in the right of this vectorial equation.
Okay, so you're all saying things that are correct, but not in the correct order of logic. There's a thing that the inverse does not exist, right? That is basically the same as saying that the determinant is 0, right? But the first thing that happens that implies that the matrix has no inverse and the determinant is 0 is
not the diagonal element.
Not necessarily.
No, it's implicit.
Carlos?
I will give a clue that the columns...
Carlos, could it be that if we have a 2D matrix, but we have a 0 row or 0 column, then we are projecting, if we multiply that by a vector, we are projecting it into, we're basically eliminating like a dimension?
Yes. In this particular case, we have a problem with the column 0. But why we have a problem with the column 0? It's true that we remove a dimension, but how we can say that mathematically?
It's linear dependent.
Exactly.
One is linear dependent of the another.
The reason that the A matrix has no inverse is that the columns columns. I think I missed a letter. Whoops. Let me double check. Yes. Columns are linearly dependent. If the columns are linearly dependent, that means that there's no inverse. And
right.
The inverse of the matrix can be written as some operation that I will not talk about, divided by the determinant. And if the determinant is 0, this expression does not make sense. So everyone said something that it was kind of true, but the main reason is that the columns are linearly dependent. And by definition, the column 0 is linearly dependent. Why? Because if I have a vector x alpha plus beta times 0, there's a way in which I can make this equals to 0 with all this different. Yes. B could be, for example, 2, and the first one could be alpha equals to 0. So not all the coefficients are equal to 0. And well, this is a little bit incorrect. The 0 vector by itself is not linearly independent, but it's linearly independent if I have a collection of any vector x and 0. The collection 0 whatever is linearly dependent. So that's the main reason. In the case that a column is 0, that means that we have a loss of the dimensionality, but you could have the case of a matrix 1, 2, and 2, 4, in which the columns are linearly dependent, all the coefficients are non-zero, and the inverse of this matrix does not exist. So in this case, the inverse of the matrix does not exist. Being A equals to this. Oh. So everything clear?
Yes.
Yes? Okay. And what happens if I have a linear transformation that is, for example, 1, 0, 2, 2, 0? Basically, I lose all the information in the y component. So the image will look something like this. It actually would look like a line, but I am repeating the image multiple times. That's why you see a line with repeated values when you go up.
That is the output for the girl picture?
Yes. So if I do 0 and 1, I have this. If I now do the transformation, all the elements will collapse to one dimension, like this. So I have a loss of information here, therefore this transformation is non-invertible. Okay, so that's good and all. And how can we apply this intuition to solving linear systems? Oh, by the way, when the columns are linearly dependent, you can define something that is called the rank of the matrix. Well, not only the case that the columns are linearly independent. For every matrix, there's an operation called the rank of the matrix that will give us the number of columns that are linearly dependent, or basically there are no problem with those columns. In this case, the rank of this matrix is 1, because only one column is linearly independent. If I remove the 0 vector, I have a linearly independent set with one vector. And when the rank of the matrix...
That is relationship with the span?
Yes. The rank of the matrix is like the number of dimensions that the matrix can represent. And it always, to have an inverse, it needs to be equal to the dimension. In other words, if the matrix has a span that is the same space, or saying it the other way, if all the linear combinations with the columns of the matrix represent the whole space, that means that the rank of the matrix is equal to the dimensionality of the space. If instead of representing the whole space, it represents only an hyperplane or a lower dimensional space, the rank, it will be inferior, and basically you are by applying that matrix, you are having a loss in information, because you're collapsing the whole space into a plane or to a subspace. That is the problem. So you can quickly check if the matrix A has an inverse if the rank is equal to the dimensionality. In this case, the rank is 1, and it should have been 2. So if I have this matrix that is n by n, and I apply the matrix or the linear transformation to a vector n in the same way we have been doing it, and I have a result of b, to solve this system, that means to find x having b, let's say v is our image that is rotated, for example. How can we find the original image having the rotated image? And we can solve this only if the square matrix has full rank, or the rank of the matrix equals to n in this case. And we can do that by using linear algebra that solve. This is a package from NumPy. NumPy linear algebra.solve. Let's see an example. I have a matrix here that is 4, 3, minus 5, and 9. And the result of applying this matrix to a vector x equals to 20 and 26. I want to solve for x, and I use here the function solve with the matrix and the vector. And, sorry, matrix rank has not been imported. There. Let's see. The rank of this matrix is 2. That's good because the dimensionality here is 2 as well. That means that the matrix is it has a full rank. And the solution that this solve function gave me is 2 and 4. And if I do a times x minus b, that is the same as the 0 vector. So that means that this x vector is in fact the solution of this system. Now, if instead of minus 5 and 9, I do, for example, 8 and 6, or minus, and it will say that this matrix is a singular matrix. Okay? A singular matrix is the name of a matrix that the rank is not the same as the dimension, or that means also that the determinant of the matrix is equal to 0. So basically we cannot solve the system if the rank of the matrix is not the same as the dimension. Let's remove this minus sign, so now the columns are linearly independent, and there's a solution of this system. Okay, so how can we solve when we have a matrix A that is not invertible? How can we get an approximate solution of what was the X? And for that, we will use what it's called the pseudo inverse. Okay, sorry. First, when you have the same full rank matrix A, you can also, instead of using solve, this would be the same of calculating the inverse of the matrix and then using the dot product with the vector V. I must say that this is inefficient, because we do not need to calculate the matrix A to solve the system. This has the disadvantage of calculating, storing, sorry. Hello? Are you still listening to me?
Yes.
Yes, yes. Oh, okay. So I had a message that there was some error with my internet, so. Okay, so just to repeat the fact that I was saying. What? Inefficient. Okay. Yes. To solve this kind of systems, we do not need to calculate the inverse of the matrix. We can just solve, and we'll be more efficient because we are not calculating nor storing the inverse of the matrix. So this is equivalent, but this is not recommended. Always use this. Okay, so when the matrix is a non-square matrix, or the matrix is not a full rank matrix, we can solve the system by obtaining the least squares solution. The least squares solution tries to solve this optimization problem in which you try to find an x that minimizes this ax minus v, and then it calculates the norm of that vector, or the length of that vector. In the case of full rank or square matrices, this problem is equivalent to calculating the inverse. When we do not have a full rank matrix, or is a non-square matrix, you need to solve it this way. And the solution of this problem, I'm not sure if you have seen it in class, is to use the pseudo inverse. But if you don't want to see what that means, you can use the least squares function in Python. For example, I have here a matrix 0, 1, 2, 3, all ones, a vector here, and an x. And if I calculate the least squares solution to this problem, basically what I was doing was calculating a linear approximation of the data. The original data was these blue dots, and I was calculating the slope and the intercept of this line. This is a very common problem in science, and to do it we need to solve the least squares problem that behind the scenes is basically multiplying by the pseudo inverse. Okay, so this is a method that can be used for every function or matrix. If you do the pseudo inverse of a regular matrix, a full rank matrix, you will get the same solution. So this is a general solution to linear problems. And the solution we find has the main characteristic that it minimizes the length of the obtained vector. You can also get another types of solutions that I will not get to in this TA, but this is as a first approximation is a very good solution. All right. And obviously you can do the pseudo inverse as well, but this is not recommended because you have the same problem. You have to calculate the pseudo inverse and then multiply by the pseudo inverse. So this is not an efficient. Do not do. Use least squares. But you'll get the same exact solution. Okay. So we have an activity, but I'm not sure if we have time. It's very similar to the one in the homework. So I'll just skip it and talk a little bit about the Svd algorithm. Some of you could probably have heard of principal component analysis, PCA. The principal component analysis algorithm or procedure uses the representation of a matrix or a matrix of characteristics in a space that is called the eigenspace. Or eigenspace, because it's a German word. This eigenspace is the one that you obtain after applying the SVD procedure. That is similar to the QR decomposition, but instead of having two matrices, Q and R, now you have three matrices, U, S, and B, that have very interesting properties because U and B are orthonormal bases, or the matrix is normal. And also this S matrix is a diagonal matrix that has the singular values of the matrix. This is equivalent to this series, but let's look at it with a picture, maybe a little bit smaller. Yeah, there. So I have a matrix M that is not a square matrix, and I can write it as U, this sigma or S, and this V matrix. The main characteristic of U and B are that when you multiply U and U transpose, you get the identity matrix of size M. That means that the transpose of this matrix U is the inverse of U, the same way that the rotation matrix had an inverse that was the same as the transpose. And you can do the same with V, but instead of the identity matrix with size M, you get this identity matrix with size N. And another thing that this diagonal is not a square matrix, by the way, but you have these diagonal terms that decay very rapidly. The singular values decay very rapidly. That, for example, can be applied to compress an image. If we represent our image with a matrix, and we then apply the SVD algorithm, and remove some of these singular values, for example, this last one is very small, so we multiply that by 0, we can compress the image. Here, I have a face that has all the singular values. Then I start removing singular values. That means that I need to save less memory. This is a compression. And I start to lose information, but there's a point that is, for example, here, that I have removed 900 of the singular values, but you still have a decent face. This is called in this example, what I'm showing here is the Eigenfaces. That is an algorithm used to do face detection. So basically, in all the smartphones now you have an unlocking mechanism that is like facial recognition. Behind the scenes, it's doing something similar to this. It is compressing your face into an eigenface, and then it's comparing that eigenface to the one you stored. And if they are sufficiently similar, then it unlocks your phone. Yeah, you can do this with images, with just characteristics. That's where the principal component analysis comes from. So it's a very handy process. Okay, so let's leave the recording here, and you can ask more questions in Spanish afterwards.